Welcome to the fifth episode of the THETIDA webinar series titled the Coastal and Underwater, sorry, not this one. Sorry, give me a minute. Yeah, titled Remote Sensing and Photogrammetric Techniques for Cultural Heritage and Environmental Monitoring. It is with great pleasure to welcome our esteemed guest speakers. Miss Lia Karathanasi, Vasilia Karathanasi, professor at the National Technical University of Athens, and Professor Andreas Georgopoulos, which is also an emeritus professor from the National Technical University of Athens. Before giving the floor to them, I would like to first give the microphone to my colleague and the day-to-day project manager of THETIDA, Dr. Panos Michalis, for a small welcome. Panos.
Yeah, hello everyone, and thanks for joining this webinar. Remote sensing is one of the core components and services that are being developed as part of the project, of our project in THETIDA. So we're looking forward to listening to the two colleagues that have decided to provide the two talks today, the Professor Vasilia Karathanasi, who is the Director and Professor of the Remote Sensing Laboratory of the National Technical University of Athens, and Professor Andreas Georgopoulos, who is an Emeritus Professor of Photogrammetry and Heritage Recording at NTUA. So without any further delay, Dimitri, I pass the floor to you in order to start the webinar.
Thank you, Panos. Professor Karathanasi, if you can share your screen. Until you do so, let me share some things regarding your bio. Vasilia Karathanasi, Director and Professor at the Remote Sensing Laboratory of the NTUA. She earned her degrees from NTUA as well as her master and her PhD, and her master from Paris Sang. She specializes in hyperspectral and multispectral remote sensing, machine learning, and time series in INSAR. She will elaborate further one part of her expertise in today's webinar. And she teaches multiple undergraduate and postgraduate courses, and of course, she has supervised numerous theses. So, Professor Karathanasi, the floor is yours. We cannot wait for your presentation. Thank you very much for being here. And just to add that NTUA is a partner on our project with a very crucial role. So, thanks for everything that you have done so far.
Thank you, Dimitris. Hello, everyone. What you are about to hear is not an April Fool's joke, but the contribution of remote sensing to the preservation of cultural heritage. Remote sensing is recognized as a powerful tool for cultural heritage using multi-platforms such as spaceborne, airborne, aerial, UAV, and ground-based platforms. Multi-mode sensors such as hyperspectral, multispectral, synthetic aperture radar systems, LIDAR systems, digital cameras, and ground-based sensors. And by analyzing multispatiotemporal observations. Remote sensing for cultural heritage includes a list of technologies such as photogrammetry, LIDAR, Earth observations, and geophysics. The information derived by these technologies can be managed and integrated into GIS, databasing, WebGIS, and web app tools. We cannot, of course, overlook the transformative role that artificial intelligence now plays in the analysis of remote sensing data. Remote sensing contributes to the preservation of cultural heritage in two key ways: by monitoring the dynamic changes in the surrounding environment that immediately or gradually affect cultural heritage assets, and by detecting degradation that affects cultural heritage assets. With respect to sensing dynamic alterations in the surrounding environment, the Remote Sensing Laboratory team of the National Technical University of Athens has developed 6 tools which can detect, map, monitor, and often predict key changes, mainly related to climate change. Ground deformation, changes in permafrost thawing dynamics, and inundation prediction tools relies on time series synthetic aperture radar interferometry. The flood mapping tool relies on the processing of time series synthetic aperture radar images, while shoreline dynamics and impervious surface growth mapping tools rely on the processing of very high resolution multispectral images. With respect to sensing degradation that affects cultural heritage, hyperspectral imaging technology can assess this material degradation, while close-range photogrammetry, terrestrial laser scanning can assess detachment of material, structural instability, and material loss. Of course, moreover, these technologies are the key technologies for implementing 3D documentation. In this presentation, I will present the biological and chemical material degradation, while the other three modules, tools that are crack detachment, structural stability, and material loss will be presented by Professor Andreas Georgopoulos in the second part of this webinar. The ground deformation tool allows us to predict whether monument is at risk of subsidence or tilting. What is ground deformation? Ground deformation is a change in shape of the Earth's surface, manifesting as subsidence, uplift, or horizontal movement. One way to estimate ground deformation is to use two synthetic aperture radar images taken by the same point. The phase difference of these two images is related to ground deformation. Nowadays, instead of looking at the formation between just two scenes, we combine many synthetic aperture radar pairs, which form an interferometric stack. To estimate with this stack, we can estimate land deformation more accurately and track how displacement evolves continuously over time. We estimated ground deformation in Rhodes City, where among other monuments are the St. Nicholas Lighthouse and the Lilac Pier, both part of the medieval fortifications, the Roman Bridge, which is one of the few ancient bridges surviving in Greece, and the grave enclosures in Rodini, dated in the 3rd to 2nd century before Christ. We estimated the ground deformation using STAPS functionalities for the period 2016 to 2019. Green points in the left image show no ground deformation, while blue points show an uplift that is mainly controlled by tectonic processes. The grave enclosures in Rodini lie within the area characterized by tectonic processes. Therefore, continuous monitoring of these monuments is required to prevent possible structural instability. The first two plots in this slide illustrate the stability of the ground on the areas where the three monuments, St. Nicholas, the Nyack Pier, and the Roman Bridge are located, while the plot at the bottom illustrates the uplift of the terrain at Rodini in millimeters, revealing the speed of tectonic uplift over time. This was the subject of a video that was made by EuroSea and was selected as one of the 3 finalist films in a competition organized by UNESCO. We also studied the ground deformation in the IJsselmeer in the Netherlands. The IJsselmeer region features premier UNESCO World Heritage Sites, highlighting Deutsche water management. The region showcases centuries of efforts to combat the sea and reclaim land through the creation of polders. In the area, there are watermills, polders, historic dikes, historic canals, traditional villages, and the historic Cemal de Poel pumping station. The area is below sea level, so water must be continuously pumped out to keep the land dry. When groundwater levels are artificially lowered, water pressure in the soil decreases, clay and peat compact, and the land surface sinks. Land subsidence is evident in the plot of this slide, where orange points show significant subsidence from 2019 to date. I move on to the next remote sensing tool, which is monitoring permafrost using INSAR time series. Permafrost is the ground that remains at or below 0 degrees at least 2 consecutive years. The top layer, active, which is called also active layer, thaws every summer and refreezes in winter. Therefore, in Arctic, we expect a seasonal ground deformation within the year, like the one we observe in the left plot. When ground deformation is like the one we observe in the right plot, there is a degradation of permafrost. That is, the permafrost is thinning. In the image on the top, you can see in gray the permafrost and in brown the active layer. The image shows 3 stages of permafrost degradation, with the third one here, where the permafrost is totally degraded. Permafrost, we monitor the dynamics of permafrost in Svalbard in Norway. Permafrost in Svalbard is experiencing rapid changes due to intense Arctic warming. The changes have an impact on the reshaping of landscapes and directly affect cultural heritage. In Yortam, there is a coal cableway station that in 1917 was used to transport coal from the mines located in the mountains down to the harbor. It is considered a monument of industrial heritage. Interpretation of the ground deformation plots reveals whether permafrost degradation is occurring. Regions A and B in the first 2 plots shows subsidence signals in the period 2018 to 2024, because the best fit line shows a clear downward trend. Regions A and B are here and they are close to the cableway station, which is somewhere here. Region C exhibits a drop of about 25 millimeters at the end of 2021, and that can be related to landslide activity. The third tool, the inundation prediction tool, relies on altimetry data and prediction and absolute sea level rise predictions on subsidence estimates and on digital elevation models. Relative sea level rise is estimated by subtracting future land level, which is here, from the future sea level. The tool is very important for coastal cultural heritage. Using this tool, we created inundation maps for the island of Mykonos. Perhaps many of you don't know that in Mykonos town, near the coast, lies the castle of Mykonos, which was a fully fortified city until the beginning of the 15th century. By the 19th century, the castle lost its defensive importance and gradually fell into disuse. Based on the relative sea level rise predictions over the next 10 years, we propose the inundation depth index, which is an estimate of inundation risk. According to this index, a low inundation risk is presented in the island of Mykonos, and it's depicted in yellow. In contrast, in the coastal area of the Ayseemir, some points exhibit a serious risk of inundation and are shown in red. The next tool is the flood PI, which is the flood mapping post-event tool. Flood mapping with synthetic aperture radar imagery relies on the fact that water acts as a specular reflection and the signal does not return to the radar antenna. Flood PI tool uses two pre-event and one post-event Sentinel-1 SAR images and FlatVid, that is a visual transformer model trained on Curo and CUO datasets. This slide presents the results of the flood PI tool when used to monitor the major flood in Thessaly in 2023. In dark blue, you can observe the extent of the flood on September 7th, while in light blue, you observe the flooded areas on September 13th. In the flooded area, there are two cities, Pharkadon and Vlohos cities, both existed in the classical period. Their preservation is important because they help us to reconstruct the political geography of ancient Thessaly. I move on to the next tool that helps us to monitor changes in the coastline. The tool uses very high resolution imagery, and if in this case that we used Sentinel-2 imagery, we super resolved it to obtain a very high resolution image, then uses the segformer model architecture to segment the image into two categories, land and water, and the contour extraction algorithm to extract the shoreline. When we apply this tool in two different dates, then we can compare the extracted shoreline and calculate the retreats and accretions of the coastline over time. This slide shows an example of applying the shoreline dynamic tool to the coastline of Mykonos. We implemented it in two different years, in 2015, and the extracted coastline is in red, and in 2023, where the extracted coastline is in yellow. By using these transects on the two that cut the two extracted coastlines, we can calculate the erosion of the coastline in this period. Similarly, a coastline retreat is observed here, where the cable station is located. The table on the right shows retreats, accretions calculated along the cross sections. The next tool allows mapping the growth of impervious surfaces. Impervious surfaces are buildings, paved roads, and parking lots, all related to urbanization. Although impervious surface growth does not have a direct impact on cultural heritage, it is associated with various types of hazards that may affect it, such as flooding, ground subsidence, urban heat island effects that lead to thermal stress on materials, air pollution concentration, which lead to chemical weathering of stone, traffic vibration that leads to structural damage to monuments, and microclimate alteration and ecological degradation. The tool we developed is based on the bitemporal spatial relationship concert network, a deep learning architecture designed for change detection. We implemented the tool to map changes in the ICMIR during the period 2016 to 2023. In the left image, you see the two images that were obtained from the built material data platform, the manually labeled changes, and the model predictions. In the right image, red color represents the changes in various surfaces. Their impact in ICMIR may be increased runoff and pressure on drainage systems, fragmentation of historic polder geometry, and visual and structural pressure on historic infrastructure. This slide shows changes in pervious surface in Mykonos between 2016 to 2023. With viewed black lines is the hydrographic network extracted from the ALOS pulsar digital elevation model. We observe that some impervious surfaces are constructed over streams, modifying the natural water flow and increasing the risk of flooding during storm events. I move on to the tools related to the detection of degradation affecting cultural heritage assets. I will focus on hyperspectral technology that allows the mapping of biological and chemical material degradation. The tool is based on spectral mixing. Most pixels in an image are mixed pixels. In the middle, you observe the area on the ground represented 3 by 1 pixel. This pixel contains a mixture of 3 materials. According to the linear mixing model, the spectral signature of a mixed pixel is the linear combination of the spectral signatures of pure materials present within the field of view of the detector. Pure materials are known as members, and spectral mixing breaks down the composed mixed pixels into pure materials and determines their corresponding proportions, known as abundances. It requires hyperspectral imagery to provide more accurate results. Pure pixels may represent land cover categories or specific materials, depending on the spatial resolution of the image. The example above shows a land cover image, the extracted end members, and the produced abundance maps. Each abundance map shows the relative prevalence of a land cover category across the scene. Similarly, the example below shows the image of a surface and the abundance map of the materials that compose the mixed pixels of the image. Spectral mixing was applied to a section of the wall of St. Nicholas Fort to map its materials that are marble, stone gray, stone reddish gray, and stone red. The materials of the asset exhibit physical degradation caused by abiotic factors such as wind, water erosion, and land abrasion. However, this type of damage cannot be assessed using spectral mixing. It is close-range photogrammetry that provides estimates of material loss caused by abiotic factors. In this study, the results of the mixing procedures were combined with the material loss estimates to assess the vulnerability of each material type. This is shown in the table on the right, where you can observe 4 levels of degradation and the degree of degradation of each material. Spectral mixing was also applied to a section of the wall of the castle of Mykonos. Materials were iron secretions, marble, brick, a gneiss and cranidoid, mortar and shadows, and an iron bar. The iron secretions resulting from the iron bar embedded in the wall are considered chemical degradation, whereas the other members correspond to the wall's constituent materials. I will conclude my presentation with two examples of spectral mixing in underwater cultural heritage. The first concerns the Equa's wreck. The Equa was a submarine chaser that sank while patrolling the coast of La Spezia on 10 June 1944 after colliding with another ship. Spectral mixing identified steel, iron secretions, carbon, sand, and cells. The material of the asset is steel, while carbon and iron secretions represent chemical degradation products. The second shipwreck we studied is the Niskia shipwreck. This is a wooded Ottoman shipwreck located off the western coast of Famagusta Bay in Cyprus. It is located in 28 meters at 28 meters depth, and the underwater landscape is flat-sided seabed and Posidonia fields. Spectral mixing indicated that the shipworms are the main factors in the degradation of the wooden ship because they feed on it. Using close-range photogrammetry, material loss was estimated and classified into three classes: low, medium, and high degradation class, represented in brown, gray, and black colors. With this slide, I conclude my presentation. Thank you for your attention. If you liked our work, you can visit the activities of the Remote Sensing Laboratory and the THETIDA project on LinkedIn and on other social medias. If you have any question, please do not hesitate to ask me. Thank you again.
Thank you, Leah. Great presentation. A lot of food for thought, I would say, for today and for every participant that follows today's webinar. And I think we will keep the questions at the end after Professor Georgopoulos' presentation. So let me now pass the microphone to Professor Georgopoulos. Professor Georgopoulos, if you can please share your screen. Professor Andreas Georgopoulos, Emeritus Professor of Photogrammetry and Heritage Recording at NTUA, holding a Diploma of Surveying Engineering from NTUA, and a Master and a PhD from the University College London. Since 1980, he has been teaching photogrammetry and documentation of monuments at an undergraduate and postgraduate level in various universities, UCL, NTUA, and as a visiting professor at K. Leuven, CAT, and the University of the Aegean. His research interests focus on 3D modeling, on cultural heritage, photogrammetric automation, and digital contemporary techniques. And of course, he has participated in numerous research projects funded by the European Union. Without any further ado, I would like to give the floor to you, Professor Georgopoulos, to thank you on behalf of our consortium that you were present today. It's an absolute honor for us, and we cannot wait for your presentation.
Thank you very much. Make sure that you hear me. Is that okay?
We can hear you loud and clear, and we can see also your presentation.
Okay, perfect. Thank you very much for the invitation and for the opportunity you give me to present some of the research that we have done in our lab concerning cultural heritage. I will confine myself to explain two key technologies for the documentation of cultural heritage, justify why we must geometrically document cultural heritage, and I will show you three examples of the projects that we have done. So, as you know, cultural heritage is in danger, in great danger, for a number of reasons that we see here. And I have some examples. This is a fine example of looting. You can see the iconostasis, and some ancient or very old Byzantine pictures are missing. So somebody broke into the church and stole the icons. This is another example of a natural disaster very close to Athens. It's about 30 kilometers from here in Vravrona, and it floods every 5 or 6 years systematically. So you see half of the temple is submerged into water. Another example is the destruction, some natural destruction by earthquake. This is a town with earthen architecture, a very important one, in Bam in Iran. And you can see above is before and below is after a terrible earthquake that happened something like 15 or so years ago. A similar example from Kathmandu, Nepal, before, left, and right after the terrible earthquake of 2015. And I had the opportunity to visit Kathmandu in January, and they have reconstructed most of the buildings of cultural heritage there. Of course, as you know, humanity is suffering also from other reasons like war conflicts, and this is a very well-known picture of what happened in Palmyra by the ISIS people. And human indifference can also lead to destruction, and this is the Notre Dame in Paris during the fire that happened some 5 years ago. So all these are examples of destruction for cultural heritage, and we, of course, believe and we know that cultural heritage is feeding our memory, and we have to conserve it and we have to protect it. So there are also international conventions and international agreements that cultural heritage is in need of documentation, any kind of documentation, accurate measurements, monitoring, proper management, preservation, and most importantly, public outreach. So this means that we have to raise the awareness of the public. Now, my presentation will confine itself to the geometric documentation, to measurement of shape, size, and position of the cultural heritage assets. And it is, as you probably know, a very important action that we have to do before any intervention. Actually, it was firstly agreed upon by humanity, I would say, or the civilized countries in 1964, that's even 62 years ago, by the Venice Charter. And in Article 16, it literally says that before we do any act of intervention for preserving, protecting, or whatever, cultural heritage assets, we must document, we must record the existing situation. So the geometric documentation, as we envisage it, is a subset of the integrated documentation, the holistic documentation of cultural heritage, which includes bibliographic documentation, historic, architectural, cartographic, legal, archaeological, any kind of documentation that you might think. Now, geometric documentation of monuments is defined or implies all the actions for acquiring, processing, presenting, archiving, and storing the data, the necessary data, in order to determine the position of the monument, its true form, shape, and size in 3D space at a given moment in time. This last remark, at a given moment in time, means that if we repeat all these actions of acquiring, presenting, etc., for determining the position and the shape and the size of a monument every, let's say, 1 month or 1 year or whatever, we monitor the monuments. Okay, we can also monitor the monuments. So now we have in our hands some very innovative digital technologies. Well, innovative, they are already with us something like 15, 20 years, but they are always developing. So I could, let's say, briefly mention the digital cameras, not only optical, but also thermal and cameras that record outside the optical spectrum. Professor Karathanasi has talked a little bit about that. We have scanners, not only laser scanners, but also other kinds of scanners. And in one of the examples, I will show you a different kind of scanner. We also have GNSS, that's satellite navigation and positioning systems. We have 3D printers. We can manipulate digital data, any kind of digital data, by powerful computers and very smart software. Okay, lately, I mean, the latest development is that we can integrate all this information, be it geometric, be it historic, be it text or whatever, into large systems that are called building information modeling, or better, historic building information modeling, so that we can manipulate the information. It's actually a 3D GIS in a very simple form. I could explain that. This is actually the trend of the time. So these digital technologies have brought automation, which is not always good, okay, automation, because it's good if we can control it. It has given us speed of all the actions. That's good in a sense. We have improved our accuracy, and this is really a very important characteristic. And most importantly, according to my opinion, we are in a position to produce alternative base material for the people who study the monuments, because actually what we do with the geometric documentation, we provide the base material on which the other specialties like archaeologists, architects, or conservators are doing their studies. So this is an interesting diagram, and I will explain it briefly. On the x-axis, you can see the object size. As we go from left to right, the object is becoming bigger and bigger. And on the y-axis is the complexity of the object, which means that we need more points to describe its geometry. And you see the various methods that we have in our hands. They cover some areas to tackle, let's say, small objects or big objects, few points needed or more points needed. Needless to say that as we go diagonally from lower left to upper right, we change the scale factor. The lower left is small scale factors, that's large scales, and upper right is bigger scale factors, larger scale factors, that means smaller scales. So we have the tactile methods and the topometric methods that we use, let's say, either our hands to copy something, to document something, or just a measuring band. We have tachymetry, geodesy, and we have also the satellite navigation. And on the upper part, you see close-range photogrammetry and 3D laser scanning. And then as we go to the right, aerial photogrammetry and airborne LiDAR. And we also have satellite remote sensing that we heard so many nice things from Professor Karathanasi earlier. Lately, we also have these toys that we fly above the ground up to 100, 150 meters or even lower, the UAVs or drones as they are called. So they also cover some area depending, as I said, on the size of the object and on its complexity. There is a distinction between those methods, the yellow ones and the blue ones. I'm sure that many of you have understood that the blue ones are using images, while the yellow ones do not. Okay, so with the blue methods above, we take an image of the object. And it's not strange to understand that laser scanning is also an image of the object, because some people might say laser scanning does not use images. No, it does. It is actually a 3D image of the object around us. So you see that we have all these methods in our hands. I will confine myself in explaining photogrammetry and laser scanning in the next few minutes. So what is photogrammetry? Of course, there are a lot of definitions, or there is an official definition, but I like to explain photogrammetry with this image. You see, this is a camera, of course, a photographic camera, and in the core of this camera, there is a guy who is an artist, which means that we have to take proper images, nice, correct images, but he's also measuring. As you can see, he's holding a pen or a measuring thing, and he also measures. So we need to take proper images and make measurements on these images to apply photogrammetry. So this is the simplest, let's say, definition of photogrammetry that I like very much to include in my presentations. Now, how does photogrammetry work? It copies nature. So it simulates human vision, and this is a human, and as you probably have realized from your early years, you sense depth with your two eyes. Okay, so we understand depth. We humans understand depth because we have two cameras, that's two eyes, and we take two pictures, overlapping pictures of the surrounding area, and we have our brain to fuse those two images and understand depth. Okay, now what photogrammetry is doing is fooling the brain by bringing in front of the eyes, the cameras, two images, and let the brain fuse them into a 3D model, a 3D perception. So actually, in its simplest form, photogrammetry brings two images, suitably taken images with overlap, etc., a stereoscopic pair, and lets the brain fuse them into a 3D model. And there are instruments to make measurements on the images and transform these images with simple geometry to the position of the points A, B, and C, whatever, a thing that we cannot do with our eyes. We cannot perform accurate measurements with our eyes. Okay, so photogrammetry copies nature, but it adds also the measurement dimension into the process. Okay, actually, we try to describe a natural phenomenon, that's the stereoscopic vision, by some geometry and some mathematics. And based on these mathematics and on measurements on images, we take we determine the position of objects in the 3D space. And of course, for that, we use cameras, which used to be called terrestrial cameras for terrestrial photogrammetry. We also have aerial cameras for mapping, etc., etc. And I show you some very, very old examples. You can see how old these are by the haircuts of these two persons there. These are special cameras that were produced in the past, about 50 years ago or something, but they are not produced anymore. So we are not bound to very expensive cameras. We use modern cameras off the shelf that you can buy from a photography shop, etc., etc. We also use simple point and shoot cameras or some industrial cameras, or we can even use underwater systems. And one of the examples is the application of photogrammetry underwater that I will show you. Well, some bold people also use their smartphones for photogrammetry, but I wouldn't recommend it at this stage of development of the cameras because they are not as powerful as normal DSLRs or mirrorless cameras so far. Of course, you can do it, but with less accuracy specifications. Now, the modern thing that happened is some very useful algorithms that we borrowed from computer vision. And one very important algorithm is the one called structure from motion, which means that was firstly introduced in 1999, if I'm not mistaken, by an American university. And they collected a lot of tourist images from the internet, and they applied this structure from motion algorithm, and they built, as you can see here, the 3D of the Colosseum in this case. It was a bigger project called Build Rome in a Day. Okay, and this is the algorithms that we use today. We mainly use today, not that more traditional photogrammetry is not used, mainly for mapping, but for cultural heritage applications, we use this structure from motion algorithm, which actually is almost automated. And what it does is finds points on the images automatically. And from these points, it finds the correspondences between adjacent or neighboring images and estimates the positions. That's the orientation. And for those of you who are, let's say, familiar with photogrammetry, it has a relative and an absolute orientation of the images in the 3D space, while if we ask it to do it, it also determines the internal geometry of the camera or the cameras that have been used. This is the self-calibration part. The steps of this algorithm, I mean, it's not only structure from motion, but it's also multi-view stereo that is another algorithm that is being used by these automated software, is to find point on images independently from one another, then establish correspondences to neighboring images, determine the relative position of the images, that's the relative orientation. At this stage, we usually apply scale and georeference with some known control points. And then we, the software is using the MVS, multi-view stereo algorithm, to produce a dense point cloud. And then from that dense point cloud, which is colored because we have very reliable color information from the digital images, we can produce a surface, a mesh, apply texture, have a 3D model, or from the dense point cloud, we can also produce some 2D products like orthophotos and sections, etc., etc. Okay, on the right you see two pairs of images, one with a lot of correspondences, a lot of blue lines connecting conjugate points, and the two images on the bottom, they don't have any common point because they are too far apart. Just a very quick example. In 2010, that's 16 years ago, I was in the British Museum, and I took these 13 pictures of this horse head. That's from the Parthenon marbles, and I uploaded them to a service that was available then by Autodesk. It was called 123D Catch. It's not available anymore, and in about quarter of an hour, I got this video back. I got this 3D model back. It's very impressive, I know, but it's full of artifacts, of problems, okay? Firstly, because I didn't take the correct images, and secondly, because the algorithm is automated and is non-supervised and does whatever it likes. So there should be a lot of caution when we use this automated software. Now we go to the terrestrial laser scanning. For those of you who are familiar with geodetic instruments, actually a laser scanner is a geodetic instrument, a total station that is able to measure millions of points per second. So actually it can rotate around a vertical axis with 360 degrees or a horizontal axis for 270 degrees. It cannot measure through its body, of course, and by measuring the angles, horizontal and vertical angle, and the distance to each point that sends back the laser beam, it can determine X, Y, and Z of all the points. I have a video here that shows the principle with which the laser scanners work. I hope that the sound is going through. Okay, I will not spend more time, although the music was fine. I hope you liked it. Now, we end up with, by using the laser scanners, we end up with a lot of point clouds from different positions, and each point cloud is in its own reference system. So we have to combine them, and this is the action that we do after acquiring all the point clouds. We have to do a lot of processing in order to register the point clouds, bring them to the same reference system. Of course, they are in 1-to-1 scale because the distances are measured in 3D space. And this can be done either with some targets or some natural characteristic points, or using a special algorithm which is called ICP, in iterative closest point. So we end up with a big, a very large point cloud around the monument or the asset that we are scanning, but without color. And this is the main, let's say, disadvantage of laser scanners, because except 1 or 2 models now, no digital cameras are available within the scanner to reliably record color. So actually what we do is combine the 2 methods, because we have a very fast point cloud and a good, let's say, recording of the geometry, good, not accurate, because photogrammetry can be more accurate than laser scanning. If you want, I can answer that in the questions later. And we have a good description of the geometry of the surface. We combine the two point clouds. We take the best out of each one, and we take the color from photogrammetry, and we have the final 3D point clouds. Now, this is a general slide with answering what could be the possible uses for 3D models. We could use them for visualization. As you can see on the right is the Roman bridge that Professor Karathanasi was mentioning earlier from another European project that we did several years ago. We can use them for the 3D models for documentation and the production of orthophotos, 2D scaled products. We can perform 3D measurements. We can decimate them and give them to, let's say, structural engineers to run their finite element models. We can use them for virtual visits, virtual museums. I will show you an example later, for 3D printing, for producing 3D models for visually impaired persons, for virtual restorations. I have an example for virtual reconstructions, serious games, developing serious games, and whatever your imagination can think of. Now I'm finished with teaching, and now I can show you 3 examples. Characteristics examples for the use of these technologies. Now, the first one is about a statue that is in Western Greece, in Preveza, and it's a big statue. Its length is about 18 meters, and the height is something like 15 meters, and it commemorates the dance of the Zalongo of Greek women that preferred to commit suicide, fall off the cliff, because they were chased by the Ottomans. Now you see on the left that the object is, this is at the edge of a cliff, and due to the adverse weather conditions, it had suffered a lot of damages, and we were called to produce a 3D model so that they could restore the monument. So you see some images of the data acquisition campaign that we did on site. The statue was full of scaffolding, which is another problem sometimes, because they didn't want the scaffolding in the 3D model, of course. And on the lower right, you can see the top of the head of the let's say, the tallest figure. So this is the orthophoto of the monument from all 3 sides. Okay, the front side, the back side, and this is the middle one here. But what they wanted is to reconstruct the damaged parts, especially the heads. So from our 3D model, we produced a 1:5 plaster model, which, based on the photographs of the sculptor, you see a photograph of the sculptor in the middle. It was completed by a specialized sculptor nowadays, and we scanned that with a structured light scanner. You see on bottom left the image, with a specialized structured light scanner, and we inserted the scan of the completed 1:5 model to our own 3D model of the real thing. And this shows you how well it fitted. And in this way, we ended up with drawings for the people who process the stones to produce the restoration stones and put them on top of the real statue. And this is before. This is an image of the 3D model before and after restoration. It actually, the restoration actually happened while we were called afterwards to redocument. And I will show you a video of the 3D model that we produced. And as this is going to go around, and let me make a little bit faster so that we can have some time for questions. And you will see now that you will see the restored 3D model in a few seconds. Yeah, okay. Now, the next example that I have is a submerged Roman villa in the Gulf of Epidavros, in ancient Epidavros, and you can see some images of the of this sunken. It's actually a sunken city, not only a villa. And we did two campaigns there, two different projects. The one was for a diploma thesis, just a small part of that, and we used images from a tripod, as you can see. So the images contained air and water. It's about 1.5 meters below the sea surface. Okay, so these are some sample images, which means that these images are suffering from refraction. We measured, of course, several points for ground control, and then we corrected the refraction with a suitable, let's say, software that we developed. And of course, knowing the distance of the camera to the surface and from the surface to the object. And we managed at the time, that was 2012, if I'm not mistaken, 2011, we managed to produce the orthophoto of the bottom and of the walls of the villa, and by combining the two, we had the orthophoto of the whole thing. But later, in another project that we had, we decided to do a bigger part with fully underwater images, and we used an action camera, mainly an action camera, to take pictures. And this is the orthophoto of the second project with a similar resolution. But we used this 3D model further to develop a virtual visit, and maybe you will see some images of the second campaign. And we developed a virtual visit with like a virtual museum where you could visit the 3D model underwater and see some information. This is the digital elevation model, some 2D products. And this is the virtual visit. I mean, a sample of the virtual visit. We also 3D printed the villa later. I will rather go back now. Okay, to save some time. And finally, I will show you my last example is going to be the very big project we did as NTUA, as our university undertook to rehabilitate the Holy Edicule in the Tomb of Christ in Jerusalem. This is an aerial view of the Church of the Holy Sepulchre. You can see the two domes. The left one, the big one, is the dome of the Rotunda, is a cylindrical building at the base of which we have the edicule covering the tomb of Christ, and on the right we have the dome of the Greek Orthodox Church. This is a very complex monument with a lot of churches and cells and stairs, staircases. It's a very complex monument, and I recommend that it's worth visiting, of course, in more peaceful times than we have now. Now, this edicule was suffering from deformation, and on the left image you can see the steel iron cage that the British had put back in 1947 so that it didn't fall apart. But the deformation you can see on the middle one, on the middle image, the deformation of the pillars, and on the right is a sketch by Professor Corres, and it shows the large deformation that was experienced there. So actually, we were documenting each phase of the rehabilitation. We started in 2015, and we went there to do a 3D model of the existing situation, and this is part of the 3D model of the dome of the edicule. And you can see on the right the 3D model cut, virtually cut, of course, and you see the antechamber, and in the back, further to the right, is the tomb chamber. We did a lot of innovative things there. One application was our colleagues from the chemical engineering department, the School of Chemical Engineering. They were using a GPR, a ground penetrating radar, to understand and detect what is within the masonry, within the walls. And they discovered that there are remainings of the holy rock, that's the rock of the cave that Christ was buried about 2,000 years ago, more than that. And from this, let's say, measurements of the GPR, we managed to produce the 3D of the remaining rock before the masonry was opened. So it was something that was revealed to us by the measurements of the GPR. Here you will see a very short video that will show you the model that we did, and with these colors is the remaining parts of the holy rock within the masonry. Okay, and maybe I will show you how the edicule was before. You see with the steel cage, and after the rehabilitation, and I have a lot of images comparing the two situations. So it's before and after. It was cleaned, it was restored, it was structurally, let's say, reinforced, and some ortho photos before and after, and the 3D model before and after. And do I have, let's say, 3 minutes to show you this video? This is a question to the organizers.
Yes, Professor Georgopoulos, you can.
Okay, so you will see this is a video of the 3D models before and after. This is before and after, but it's a video of the 3D models, not of the real thing. And even when we finished and we gave it back to the 3 religious communities, it was impossible to visit it with in the way that we are going to visit it now. Okay, from outside maybe it's easier, but from the inside it was impossible, because after we finished, they brought again all the lamps. It was dark, And the way that you are going to see the edicule restored is unique. And it's because we had the model in our hands. We still have it, of course. And this is the antechamber restored, and you see all the marbles were cleaned and all the decoration was revealed again. And we will also go into the tomb chamber, which is underneath this ornamental door or opening. And, you know, the people are obliged to duck. Okay, it's about 130, 140 in height. And we are now into the tomb chamber, restored without any candles, without any lamps. We also opened a window in there for the people to see the you see that window in the back to see the holy rock, and on the dome, around the dome of the tomb chamber, there were some dark walls, and behind this darkness, because it was because of the smoke of the candles, there were all these excellent frescoes of the myrrh bearers, myrophores, for those who would not understand what myrrh bearers are. And they were also restored, and I'm not quite sure who is going to be able to admire them in the way that you look at them now, okay? So we are about to finish. Okay, thank you very much, and sorry if I took, let's say, a few minutes more than I should.
Thank you very much, Professor Georgopoulos. Indeed, it was very interesting what you have presented, and I think it will raise a lot of questions. So let's start directly. And of course, I would like to thank all the almost 80 people that have stayed and they have followed the webinar. Pretty promising. Let's start from a question from Mr. Georgios Papadopoulos. So, in relation to cultural heritage and environmental monitoring, which are the most important aspects we should be careful with? Which are the most common problems, mistakes? Any guidelines, advice for the best possible holistic quality results? Any one of you can take the question.
Okay, may I answer?
Mm-hmm.
Yes. So, as you have seen in my presentation, there are many environmental tools that are relying on different technologies. But a generic advice is to choose your data carefully. For example, if you have an application that needs SAR data, coherence and interferometric data, the coherence is a key factor for the success of this application. Or if you have to extract the coastline, for example, in Svalbard, you have to choose images that are not covered by snow. So then you have to apply and assess the accuracy of the method on different areas to be sure that the method is robust and to check the generalization of the method. In relation, your second question is in relation to multispectral cameras. What is your advice for the number of bands? Again, here, it depends on the application. For example, for the coastal extraction, SWIR band in the middle infrared may be very important for the accuracy of the method. But for land use changes, some bands in the visible and in the near infrared may be enough to achieve satisfactory results. Also, it depends on the application. And for your third question, which is, do you advise to use them in combination with other cameras and tools? Yes, many times the combination with other cameras is very important and produces very fascinating results. For example, when we mapped the degradation of the material, we used a hyperspectral camera, but also results from close-range photogrammetry were very important when we combined them, and we have a more complete result regarding the degradation and the material loss. But this is not, many times it does not, we cannot merge different technologies. We have to be also to study before the application what technologies will choose to combine them and to produce extra results and very useful results. I don't know if I answer your questions or if you have any more.
I think you elaborated a lot, but if Mr. Papadopoulos wants any further clarifications, of course he can write it. Of course, you can use also the Q&A session, not only the chat, or you can raise your hand and I can give you permission to open your microphone and camera if this can be an option for you. So another question from Stamatis.
Can I comment?
Yes, of course, Mr. Georgopoulos, yes.
Mr. Papadopoulos' question, because it's very interesting. The first part, the second part is very technical and is addressed to Professor Karathanasi. As far as the documentation of the monuments or the application of the technologies to cultural heritage is concerned, the biggest mistake that we do is that we think we are, let's say, the providers of the technology. We think that we know everything. And we should not, let's say, behave ourselves like, like we know everything. And we have to discuss with the people who are going to use the results of the technology and of the application of the technologies. We have to discuss what their needs are. Because sometimes we use our super duper cameras and super duper scanners and we produce something that is very accurate, very detailed, but it's useless for the conservators and the archaeologists. And so my let's say advice is to discuss with the people who are bringing the technology, and everybody should understand each other's needs and limitations. So this was a comment that I felt I should make. Thank you.
Thank you very much, Professor Georgopoulos. And also something that needs to be stated is what Stamatis Bilas says on the chat. Cultural heritage seems to be one of the most important paths left for humanity to follow in such difficult situation today. I second that. I am sure that you do so. Another question from Najam. Thank you for your insightful presentation. I would like to ask how artificial intelligence could be integrated into photogrammetry and coastal heritage conservation, particularly for mural documentation, damage detection, condition monitoring, and conservation planning. I suppose this is for you, Professor Georgopoulos.
Yes, it is for me. I didn't have time to present some examples of application of artificial intelligence and machine learning and deep learning to these, let's say, implementation of modern technologies. For example, one very important thing is that we have done some experiments and with impressive results that we can produce the final line drawing using a well-trained network. Which means that if you train your, let's say, network in a way that understands the borders of the stones or the borders of the windows or whatever, then you can get an architectural drawing out of an orthophoto. This is one application. The other application, which is several years now, I think 5 or 6 years, is the semantic segmentation of 3D point clouds or 3D models. By semantic segmentation, we should understand that we end up with, let's say, semantically labeling the various objects in the 3D point cloud, like columns, like capitals, like windows, like roofs, like gables, like whatever you feed the network with, then you get some results. And this is very, very helpful for the H-beam, as I mentioned, because you have the information, the qualitative information, you have it ready. Lately, we have also done some experiments with detecting cracks, and also there is a such activity in the Politecnico di Milano, and they have also tried to identify cracks in images and orthophotos, which is very important for the structural engineers. And one other thing that is now in progress, I supervise a PhD of a very good PhD candidate who is using text to label point clouds, to do the semantic segmentation. He's using, let's say, a description of whatever person has visited in the past or whatever a monument, and identifies words, and these words are converted to labels for the segmentation, and this does not need training, does not need human labor to label, you know, to feed the network with something that is, you know, known in order to for it to detect the various assets. So this is, and of course, Gaussian splatting and NERFs is also based on artificial intelligence, but we have not yet received any metric results out of that, and I'm a metric person, so I'm a little bit reserved on that yet. Thank you.
Thank you, Professor Georgopoulos. I don't know, Leah, if you want to add something on that.
No, Professor Georgopoulos, it explained it very well.
Yes, I think he covered every possible aspect of that issue. So thank you very much. Let me see if we have other questions. Yes, the recording, you will have it available. I have written here the YouTube channel of THETIDA, so you can find it there the next days. And I think also Mr. Papadopoulos was covered by the answers of you, Leah, and Professor Georgopoulos. And I do not see any other questions. Let me go to the Q&A session because I think they have just yes. Professors, it's from Kiran. Professors, thank you for the presentation. This is Kiran from India. My question, based on your experience, what type of parameters that we need to validate to fix the geographic boundary dimensions of the mini island which distorted, damaged some 2000 years back itself? Don't know if
Can you repeat it, please?
Yeah, of course, you can see it also on the Q&A, but I will repeat it. Based on your experience, what type of parameters that we need to validate to fix the geographic boundary dimensions of the mini island which distorted, damaged some 2000 years back itself? I think it was mentioned on Professor Georgopoulos' presentation, if I'm not mistaken.
Oh, no, I think it was Professor Karthanasis.
Okay.
She mentioned about an island that was destroyed. No?
No.
No.
No. Which island? Yeah, no. And I don't know how was this
Maybe
island
Mykonos,
destroyed.
for Mykonos, Leah.
But it's not destroyed. The castle
No,
of
but it
Mykonos.
was flooded. It says distorted, damaged. Maybe the flooding.
And
The flooding
to, okay, and to detect the boundaries of the monument.
Yeah, the
This
boundary
is the
and the
question.
dimensions. Yeah.
And by applying an edge detection algorithm or artificial intelligent networks to detect the boundaries. But, yes, but and with multispectral imagery, we can detect the boundaries. But if this is the question.
And of course, if we have multi-temporal images, I mean, from previous years, we can. You showed an example like that, yeah.
In previous years, the monument was not reconstructed. There is a preservation of the monument now, and they try to reconstruct it and to take its previous, its ancient shape and structure, etc. So in previous years, there were very little remains of the monument in the area. Now we can see better this monument. So we can track it, and we can apply its detection algorithm and see how it evolutes its the boundaries of the monument through the years. Okay, yes, we can do it. Huh?
Leah, I have granted permission to Kiran to use his microphone or to open the camera. So if he or she needs more information, of course, he or she can address it. So Kiran, if you can hear us, you can ask for clarifications, or if you are covered by the answer of Professor Katrathanasi, you can let us know.
Hi, can you hear me now?
Yes, we can hear you.
Yeah. No, ma'am. Suppose you mentioned so many things. The thing is, suppose if the decision happened because of any wars, something like climate change, floods, something like that. So we will miss some data, no, right now. I mean, what you mentioned about the previous years, somewhat we can manage, but this the flow of water, it may long term it may changes. I mean, that is that in that part of view, how can you fix the boundaries? I mean, so in your presentation, Netherlands, you mentioned about that layers, bridges, some bridge connect to dot lines in the presentation. In the same way, can you fix the boundaries for that one? Suppose if some island had some disruption because of the wars and climate changes, floods, natural way, something like that, any tectonic plate tectonics, it may discuss, no? So in that case scenarios, so that's why I mentioned very long history. So in that case, how to fix that one? I mean, sometimes it may can we go far with this literature view, so that based on that they may specify some trade network routes, something like that. They will specify some locations. I mean, can you proceed in that way also to figure out that location parts, everything? Am I clear? Sorry if
No, I didn't understand the question. Maybe
Kieran,
somebody.
maybe just a sentence or the direct question to Professor Katrathanasi in order to proceed. Can you address it just in one line?
Okay, ma'am.
You
Suppose
talk about
yes.
What we talk about? What monument are you talking about?
No, I mean most, because in Asian they have the mini port systems, ports, and their structures are there.
Ports.
Postal ports, trade routes. I'm asking about trade routes. Like you mentioned about industrial. In Norway, you mentioned about industrial mining sector, right?
The industrial, the cableway station. You mean? Okay.
Like
Yes.
the same way, if you have, suppose if you want to track that old 2000 years back, those things, how to figure out those things, that boundaries. I mean, if you mentioned about this Norway industrial, that is about 1915. So industrial heritage. So in the same way, how can you figure out the very old ancient trade and sea route trade structures, especially with respect to islands, island to island.
The cableway station was worked in 1915. Yes, 1917.
Yes.
It was working.
In the same way, suppose if you go back very old, some 1,000 years old, 2,000 years old, we may have something like same thing. We have the same thing like port systems, shipyards, dockyard. How to those structures, that heritage systems, their boundaries. I want to know that one. I hope I am clear right now.
Excuse me.
I'm sorry if I miss.
I cannot. Maybe somebody has understood the question, because
if I might help here.
Yes.
The question is, how can you determine, if I understood it well, how can you determine what happened more than, let's say, 100 or 200 years ago? We don't have any, let's say, record of the time. The only record that we can have is descriptions or sketches of visitors if they visited the place, okay? And from these very vague and very inaccurate recordings, we can reproduce what was happening. But if we don't have these, I mean, we can only, let's say, speculate, okay? Did I get your question correctly? Your
yes,
let's say,
yes, sir.
Yeah.
Yes, sir. Sorry. Yes, sorry about that. Yes.
Okay, but I think in previous years, especially in Svalbard, there wasn't the cableway station, because it with the industrial revolution and yes, with etc. It's not a very ancient monument, this one. Okay.
Okay, thank you, Kieran. Do we have any other questions from the audience? And thank you, Nico, for your comment. Do you have any other? If we do not have, I will address again the floor to Professor Georgopoulos and Professor Katrathanasi for any last remarks, comments, or something else that you need to highlight. First, Professor Katrathanasi.
I would like to thank all you that you organized the webinar, and also to Andreas Georgopoulos for his very nice presentation, and it was really very nice. And I hope that our audience has gained some insights for remote sensing and photogrammetry and for the preservation of cultural heritage using remote sensing and photogrammetry. Thank you again.
Thank you, Leah. Professor Georgopoulos?
I would like to thank for the invitation. Thank you very much for the invitation. It was a pleasure for me to have given the opportunity to present some of our work in the lab, and I wish the best for THETIDA.
Thank you, and thank you both. I think even if you were specialized or not specialized regarding photogrammetry and the other or remote sensing, any of the participants can. I must admit I am within the people that didn't know a lot of things, but the knowledge I gained today is very, very precious. And thank you for being here and for presenting and sharing your expertise. And in any case, I would like to thank all the participants that stayed till now. And of course, do not forget that our project will continue till up to the end of this year. You can follow all the accomplishments and whatever we do, the activities through our website, thetida.eu. And of course, you can stay tuned in our social media. I have shared the links in the chat. You can find us there: YouTube, Blue Sky, LinkedIn, Facebook, Instagram, or you can send us an email with more information. The recording will be uploaded at our YouTube channel the next days. And I think by saying all this, we can wrap up our webinar. Thank you all, and stay tuned for the next activities. Thank you all. Bye-bye.
I see a hand raised.
Sorry. Let me see.
Yes. It was lowered now.
Okay.
Okay.
Thank you very much. Bye-bye.
Okay.